find the volume of the solid generated by revolving the region bounded by these three curves about the y-axis. Okay. We'll start by sketching this region. That's y equals 1, that's y equals x squared, and the y-axis. So this is the kind of triangular region that we have. And what we'd like to do is revolve this about the y-axis. Okay? So, as before, what we're going to do is we're going to see what the rectangle looks like when it's revolved about the y-axis, and then try to figure out the area of a cross-section and then integrate that area about the appropriate region. So, if we draw a rectangle in this region, to use the disk method, then the rectangle is going to be perpendicular to the axis of revolution. And if you revolve that rectangle, then you're going to get a disk. So if we draw that disk here, the center of that disk is this point over here. And then the point that the rectangle touches the curve at is this point here. And that distance is the radius. And we know that the area is equal to pi r squared. So, as a function of y in this case, right? Because in order to cover this whole region, I have to move this rectangle throughout the region vertically like this. So we have to write down the area in terms of y. So in terms of y, we have x equals the square root of y, represents the curve here. So what is the distance from here to here? That's an x distance, right? Okay. So x, the radius is x. But in terms of y, that's just square root of y squared. Right? So if I simplify this, then we have the area of a cross-section is equal to pi times y. Another way to think of it, last time we talked about a of x as being the area of a cross-section perpendicular to the axis of revolution, to the x-axis. Okay, so to solve this problem, we do something similar. A of y is the area of a cross-section perpendicular to the y-axis. So in this case, the volume was I times the integral from a to b of a of x dx, or just, sorry, integral from a to b of a of x dx. In this case, this is the integral from c to d of a of y dy, where the solid is contained between y equals c and y equals to d. Okay? Here, the solid was contained between the lines x equals a and x equals b. Essentially, everything else works the same way, just like we did last time. So anyways, back to the problem. The volume is the integral of, so the boundary of the solid on the y-axis is 0 to 1. And the cross-sectional area is pi y dy. So integrating this gives us pi over 2. Pi over 2 cubic units. That's the volume of the solid described over there. Okay? last time, one revolve about an x-axis or an axis parallel to the x-axis. Everything else works very similarly, doing this about the y-axis. Okay? Now this method is fine, and it worked every time we tried to use it, but sometimes it doesn't work. So here's an example. So, find the volume of the solid obtained by revolving the region bounded by y equals 1 minus x squared. The x-axis and y-axis. Okay, these are the boundaries about the y-axis. As a matter of fact, we can change this around a little bit. This curve. Let me write. This one. That's the curve. Okay. So to start, we will sketch this region. This is a parabola where the vertex is at 1, 1. And it opens downwards, and if you solve for the x-intercepts, then you'll see that x-intercepts are 0 and 2. So the region we're talking about is this region over here. I guess the y-axis is not a boundary after all. And what we'd like to do is revolve this region about the y-axis. Okay? So we get some sort of solid here. Now, if we try to use the old method, right? The old method would be to draw. So you would get some solid that looks like this, right? And if you take a cross section, basically you could take a cross section like this, and you notice that what do you get? You get a washer, right? Which is fine, we know how to do that. Except when we're trying to get the radius, this outer radius hits this curve, the inner radius hits this curve, but they're the same curve, right? And so that finding the radius would be difficult in that case. Big R and small r are difficult. So we have to come up with another method for doing this. So this washer doesn't work, or is hard. Let's say it doesn't work well. Okay, we could technically, for this particular problem, we could find what this curve is and what this curve is, because it's a quadratic and we can solve quadratics. But if it was a cubic, for example, it would be really difficult to solve for x. So this would be really, really hard. So instead, we have to come up with another method. Okay? And first we're going to describe that method. We're going to study it very carefully, and then we will apply it to this problem. Okay? So by the end of this part of the lecture, you'll be able to solve this problem using the new method. The new method is called finding volumes of solids of revolution. Using cylindrical shells. Okay, and here's the idea. So this was our region from A to B. And I want to revolve this about the y-axis. Yes, this is a similar problem. And the curve is given by y equals to x. And we'd like to revolve this region about the y-axis. For the same reason as in the first example, if I were to draw my rectangles like last time and get washers, I couldn't figure out the outer and the inner radius of that washer. So there's an alternate approach to doing that. Instead of trying to see what a rectangle that is horizontal looks like when it's revolved, let's see what a rectangle that looks like this, what that looks like if that was revolved. If you were to revolve that about the y-axis, what would you get? Okay? So if I kind of do some symmetry over here, okay? I get the cylinder with a really large hole in it, so I just get the cylindrical shell, right? Like an empty can, where the boundary is really, really tiny, very thin. That's called a cylindrical shell. Well, the boundary is going to be as thin as this rectangle is, right? You're going to have a massive hole in it. Yes? That's called a cylindrical shell. I'm going to exaggerate the picture just a little bit so we can do some mathematics and geometry. Something like this, okay? Something like that. Okay, so we're going to call the height of this outer cylinder h. Okay? And what I'd like to do is I'd like to call the thickness delta x. Okay? So we're imagining that we're partitioning AB into subintervals of equal length. So all the subintervals will be delta x wide. Which means that the thickness out here, this thickness here, yes, is delta x. Okay? So then the question becomes, what's the radius? Okay? So, so here, let me take the middle part between these two boundaries, yes? And let me call that the radius. So that's the distance from the center to right between these two boundaries. Yes? So the outer radius will be little r plus delta x over 2. Yeah? Right? Because this thickness is delta x. But if you're going from the center to the middle of that, then to go just this leftover place, then that would be delta x over 2. Let me exaggerate that part of the picture. This is r, and this is delta x. Okay? So if I were to go from here to here, then that little part is half of delta x. Similarly, the inner radius would be equal to r minus delta x over 2. Yes? Okay. Great, so having said that, in order for me to calculate the volume here, I have to get the volume of the big cylinder as if it was full, and subtract the volume of the inner cylinder, which is the hole. So the volume of the shell, well, the volume of the outer cylinder is pi times the radius squared, which means the outer radius, times the height, which is h. Yes? Okay. Now I'm going to take away the same thing, but for the smaller one. And so that's pi times r minus delta x over 2 squared times h. Okay. Great, so let's simplify this. It's very clear that we have pi h as a common factor, so let's factor that out. And within the brackets, we can multiply this out. That would be r squared plus r delta x plus delta x squared, right? And minus r squared plus r delta x, sorry, delta x squared over 4 plus delta x squared over 4. And a lot of terms cancel. So the volume of the shell is pi times h, and let's see what cancels here. R squares cancel, right? Sorry, this is minus. Great. So R squares cancel. We have r delta x minus negative r delta x. You add those. You get 2 times 2r delta x. And then the delta x over 4 minus delta x over 4 also cancels. So actually that's all we have. Does that make sense? Okay, so the volume of this shell is, let's write this out this way. 2 pi r h delta x. Okay? Is that okay? Yeah. Okay. Now, well, r is not an abstract number. R comes from the way the graph looks. Let's go back to the graph. We're going to talk about r here. Okay? This green line. That's kind of in the center over here, yes? Because it goes to the center. So if you can draw it, you have the rectangle, you draw it right in the center. And that's where you can hit the curve if you're taking the midpoint of the subinterval to get the height of the rectangle, yes? So, so if we were talking about the kth subinterval, that's xk minus 1 xk. So this height is a function value at one of these points, or a point between these two, right? So this point right in the middle here, let's call it ck. Actually, we know from Riemann sum that it doesn't have to be right in the middle. Let's suppose it is. Taking that into account, what is the height here in terms of the function? F of ck. Yes? Okay, great. Now let's calculate the radius. The radius, if this point is xy, or actually that point is ck f of ck. Right? What's the radius then? The radius is horizontal distance. So what is the radius? ck? C sub k. Very good. Okay, so what I'm going to tell you now takes some imagination because it's hard to draw. I'll try to draw it, but you have to visualize this. If I put this back in here, so V shell, and of course I'm talking about one of the shells, just the kth one for example, is equal to 2 pi. R is C sub k, H is F of C sub k, delta x. Okay? Of course, you know what the goal is. I mean, we want to get an integral at some point, right? And this is already starting to look like part of a Riemann sum. You just add these up, take the limit. As the partition gets really small, then you have an integral. Now, before we do that, we have to actually make sure that we actually do get the whole solid. Okay? And I want you to think of Russian dolls, those ones that go, the smaller one and then the bigger one, and they go inside one another, yes? And that's the whole idea here. I'm going to try to draw this picture a little larger. And hopefully we can see the point. So something like this. So we would get something like this. So if I were to take a rectangle right here, this one over here, you know, get a cylindrical these kind of shells that kind of span out. If you do that for the whole thing, then it spans out the whole surface, or the whole volume. The actual solid kind of looks like this. These are holes. Okay? Kind of difficult to visualize, but you have this kind of two bumps and you have a hole in between. Okay, and these holes kind of look like circles. They get bigger and bigger. Does that make any sense?
Yes.
Yeah. Okay. So what we're doing is we're just taking kind of strips here and like cutting the solid this way in the circle, and then cutting it in the circle a little bigger, and that's your shell, right? And that's what you're doing. You're just cutting concentric circles that are really close to one another. And if you do that throughout the whole thing, then you get all these shells, one inside the other. But we did it backwards. We started with one shell and figured out we could do that for the whole thing. Okay, so supposing here then this point is A and this point is B. If I want to take this and do all the rectangles that generate all the shells, I'd have to add these up. Okay. So now to get the volume, so we add these up from k equals 1 to n of whatever that value is. It's 2 pi ck f of ck delta x. And then I want to take the limit as the partition goes to 0. Okay? And that's going to give us the volume of the solid. And that's the definition of an integral. We just have to figure out what the integrand is. The limits of integration are easy. That's from A to B. Yes? Now what's the integrand? Well, the integrand comes from this expression, right? So let's translate that. That's 2 pi x f of x dx. Very good. That's the formula. Okay? Of course, a lot of people write this formula. It is a constant, so we could write it as 2 pi integral ab x f of x dx. Okay? And that will give us the volume of solid revolved about the y-axis. So here's a good summary of what we have so far. When you have this for washer, when you want to use this for washer method, okay, then the rectangles have to be perpendicular, your rectangle height, I should say, have to be perpendicular to the axis of revolution. When you're using cylindrical shells, then your rectangle height has to be perpendicular, or not perpendicular, but parallel to the axis of revolution. Okay?
Did the other method work? What was that?
Which would work. I mean, it's difficult because you have to solve for x. Let's go back to the original problem. So the original problem said the boundaries were minus x minus 1 squared minus plus 1 and the x-axis. And that was the region, and we're going to revolve it about the y-axis. So again, if I were to use the disk washer method, okay, okay, I would have to draw rectangles like this so they could span out a washer, right? But to get the inner radius, I have to measure from here to here. That's a measure in x, right? And the outer radius is this point to this point. And that's a measure in x as well. Which means I need a function, x equals something with y. X equals g of y. I don't have that. I have y as a function of x. Okay? So in order to use that method, you have to solve for x. Which in this case is easy, but in some cases may be impossible. Right? Okay. So then that gave up, that method doesn't work. So we came up with this other method, where if you look at solids where the rectangle is parallel to the axis of, this is the axis of revolution. So parallel to that, okay? And what we ended up getting was washers. Sorry, cylindrical shells. Okay? Now that formula is not that useful, although that was like the big thing. What's more useful is this formula over here. Two pi r h delta x, because usually what changes is r and h every time. Okay, if you revolve about the y-axis, then that's a good formula to use. But if you revolve about another vertical line, then that formula doesn't work anymore. You have to adjust it a little bit, okay? Because the radius doesn't work. Remember, the radius is measured from the axis of revolution to a point on the curve. So if that changes, if it's no longer y-axis, if it's some other axis here or here, then the radius is going to change. So it's better to remember that volume of the shell is 2 pi r h delta x. That's how we can remember it. And then translate that to the integral. Anyway, in this case, we don't have such a problem. So we say, okay, the volume is equal to 2 pi times the integral from 0 to 2. The radius is x. The height is the function. Dx. Okay. Another thing that's nice about it is we don't have to square anything. You don't have to get the radius and then square it. We have to do some simplifying here, which we'll do. We go from 0 to 2. So if you multiply this out, then you get negative x squared minus plus 2x. That's it. Okay, and then if you multiply that by x, then you get negative x cubed plus 2x squared. Okay? And then you can continue. This is a simple integral to get the volume. Okay, let's do some practice problems now with this. So, okay, y equals x plus 2 is the region. Is bounded by y equals x plus 2, y equals x squared, about a line x equals to 2. That's my axis of revolution. About the line x equals to 2. So to start to draw a picture, x squared looks like this. X plus 2 looks like this. Yes? Okay, so about the line x equals to 2. There we go. So this is the region. The reason I can't stop there because the y-axis is not a boundary. The only boundaries are these two, the curve and the line. So that's how I know I have to take all the way down to here. Okay, so it will be useful to figure out these points of intersection now. So in order to do that, we can solve this equation. So negative 1 and 2. So that's 2, that's negative 1. And then we want to revolve this about the line x equals to 2, that's this vertical line here. Okay? So you're going to revolve this region about the line x equals to 2. And you want to use the shell method. Okay. So how do you draw your rectangle? Well, it has to be parallel to the axis of revolution. So you take a typical rectangle within this region. Yes? And then you revolve that. There we go. Okay? So, the volume is equal to 2 pi integral from negative 1 to 2, right? What do we put here? Put the radius times dx, right? RH dx, right? I told you that formula only works if you're using about the y-axis. But this is some other lines, we have to figure it out. Okay, but it can't be too difficult. Let's see. The radius is an x measure, so it's a horizontal measure. It's the distance from here to here, yes? Okay, the distance from here to here is 2. The distance from here to here is, this is x, so the rest is 2 minus x, very good. So the radius is 2 minus x. Is that clear to everyone?
Yes.
The height of this rectangle, or the shell, the height is going to be the y value of the line minus the y value of the curve, yes? Okay. The y value of the line is x plus 2, that's what y is for the line. Minus the y value for the curve is x squared. Right? That gives you the height of the shell. And so now you have the integral. Alright? Now I'll stop here. Now you'd have to multiply this out, collect like terms, and then integrate. Same question, but revolve about the x-axis. Same question, revolve about the x-axis this time. Okay?
Using shop.
Sorry?
You have to use shell method?
Yeah,
Or,
you have to use the shell.
for the shell method, doesn't it have to be parallel?
Yes,
But then if it's parallel, then it won't.
when we have a problem, right?
Mhm.
Okay, so maybe I should, this is going to be a real issue. I'm going to talk about this. I'm going to draw a big picture here. Okay, this is the region over here. Okay, now I want to revolve this about x-axis, that region. Yes? If I want to use shell method, my rectangle height has to be parallel to the axis of revolution. So that's fine, I draw one here. Yes? And we're okay. It's basically the curve here minus the curve here. That's a slight problem, but we can fix it. I'll talk about it in a minute. But then if you go past this point here, if you go past that line, and you draw the rectangle, then it no longer involves two curves. It involves the same curve. Yes? Okay, now that's a problem. But we're told we have to use the shell method. Okay, so we have to work around it. Now, everything we did when we cut up the x-axis, we can do if we cut up the y-axis and do shells that way. So I'm just going to take it for granted and write this formula here. Radius, height, dy. Yes? And you can do this if you're going from C to D on the y-axis. And this is a general formula if you're integrating in y. And you can see the thickness, the delta, is a y delta, right? It's a vertical delta. The other one was a horizontal delta, which was delta x, this is delta y. You could remember it like that. Okay, anyway, but the point is, this still doesn't work because you need two different equations if you're going to subtract something here to get the height. Yes? Okay, so I'll just write, this is 2 pi integral. Now, we want to go from here to here on the y-axis, and then from here to here. Yes? Let's figure out what this point is over here. We know what the x value is. It's -1. The x value here is 2. Yes? We need a y value. What's the y value here? It's 1. And what is the y value here? 4. Very good. Okay. So in order to set this up, we divide it into two regions. One region goes up to here, so that's from 0 to 1, RH dx, plus, that would just give us the volume of a solid that's generated in this region, plus the volume of the solid that's generated from this region would give us the volume of the solid generated by the whole region. So that's 2 pi integral from 1 to 4, this should be dy, RH dy. Okay? And the R and H in both cases are different. Okay? Well, no, the R is different. I mean, the H is different. The R is the same. Okay. So let's just figure this out over here. Okay. So let me draw that picture for you. That picture looks like this. Okay. We're just talking about. So this is -1, 1. This is 1, 1. Okay. And here's the x-axis. That's for that integral. Okay, and we're revolving this about the x-axis. This picture is this one. Again, this point is -1, 1. This point is 2, 4. That's this region over here. the axis of revolution to a point onto one of the endpoints of that rectangle height. Okay, and you know we're integrating in y. So this height is just y. Yes? Okay, so that part is easy. That's the radius. But how about the height of the shell? Okay? I keep saying shell. I should probably draw it. This is what the shell looks like.
1 1 foot.
That's what the shell looks like. Yes? Okay. Except what I would want to do is I would want to take the x value here and subtract it from, or take the x value here minus the x value here. Yes? Okay, I would need two equations, one representing this curve and one representing this curve. Yes? Well, that's not hard to do. This curve over here is just x equals square root of y. Yeah? And this curve over here is just x equals square root of y. Yes? Are we clear with that? Okay. So in order to get the height then, I will do right minus left, just like I did this in areas. So I have to do square root of y minus negative square root of y. Yeah? So the height is 2 square root of y. Okay? And that's for the first integral. As long as you get r and h, you're done, really. Okay, now let's do the second one. Again, here you want to draw a rectangle parallel to the axis of revolution. Yes? So if you draw that down here somewhere, you kind of see what the shell looks like. It's a good exercise to keep drawing these shells every time, just so you can visualize what's going on. Okay, the radius is the distance from the axis of revolution to a point. Right? Whether you take it here or anywhere else, that length is always y. It's a vertical length from the x-axis, so it's y. To get the height of the shell, you're going to subtract the x value of this curve. That curve is square root of y. And the curve on the left is y minus 2. Right? Y equals x plus 2, x is y minus 2. So then to get the height, you do the x value on the right minus the x value on the left. And that's your height. Okay? That's the radius and the height for the integral, the second integral. Okay, so let's put everything together then. So the volume equals to 2 pi integral from 0 to 1. The radius is square root of y. The height is 2 square root of y dy plus 2 pi integral from 1 to 4. The radius is again wait a minute. The radius is y. Okay. Here, so the radius is y, and the height is this expression over here. Square root of y minus y plus 2 dy. Okay? Alright, so this is a little intimidating. Let's actually do this. 2 pi integral 0 to 1. And we could throw this 2 out here and just get 4 pi. It's y to the 3/2 dy plus 2y integral 1 to 4 be y to the 3/2 minus y squared plus 2y dy. Okay? So v equals 4 pi, antiderivative is 2/5 y to the 3/2, or y to the 5/2. And that's evaluated from 0 to 1. Plus 2 pi, antiderivative is again 2/5 y to the 5/2. I'm just writing numbers down. So you should double check. I can't subtract though. You can multiply. 125 is 196. Yes? Well, you can subtract 32 over 5. That'll be nicer because then you have 64 and 72. That's the answer, I think. Okay? So that's the volume of the solid that we were talking about. I'll check the answer. Let's see. This is a problem from your book, actually. It's number 25 in section 6.2. That might give you a good idea about what type of problems to focus on in this chapter. Yes, 72 pi over 5. And FYI, the one I didn't do, the first one I just said integrate. If you want to write the answer for that one, that's 27 pi over 2. That's the one where we revolve about the line x equals to 2, the vertical line. Pi over 2. Okay? So now you have two methods. You have the dishwasher method, that's one method, right? Which is cross-section methods, basically. And then you have the cylindrical shell method. Typically, the reason we're doing this problem is so difficult when we do it this way. Actually, if we were to do this with the dishwasher method, it's much easier. Okay? Because you don't need two integrals. And you don't need to solve for x. You just use the functions as they are. Okay. So and sometimes the dishwasher method is really hard. You need the cylindrical shell method. Okay? So ideally, what you should be good at is looking at the region, looking at what the solid's going to look like, and decide which method is best. Okay? So we're going to talk about that a little bit. We'll write a couple of problems down and we're going to see what method is best. But before we do that, let's try to do the same problem using the dishwasher method. And hopefully we get the same answer, otherwise it will be embarrassing. Okay, so it's the same picture. I'm just going to kill these rectangles because they're the wrong orientation. Okay? Wrong orientation. So we want to revolve this about the x-axis, right? Yes? Yeah. So to use this dishwasher method, I'd like to draw a rectangle whose height is perpendicular to the axis of revolution. So this is how we draw the rectangle. And then if you revolve this it's very clear that you get a washer. Yes? And the nice thing is, anywhere in that region you draw this, the top of the rectangle always hits the line, the bottom of the rectangle always hits the curve. So you just need one integral. Yes? Even if you move this across, it just gets smaller and larger, but the top and bottom have the same boundaries throughout the region. The thickness is an x, so this is an integral of x. All we have to figure out, let's write down what we're doing. Using this washer method, the volume now is pi r squared, right? Minus r squared. So just to remind you, this would be pi times the big R squared minus the little r squared dx, or dy. Just a reminder. Okay, here the outer radius is the distance from the axis of revolution to the top of this rectangle. It's a vertical distance, it's a y distance, yes? And for that curve, y is what? X plus 2. with the curve. And then the little r, or the inner radius, is again distance from axis of revolution to the bottom one. What is y? Y is x squared. It's a vertical y. So then, this on the x-axis, this solid lies between -1 and 2. So integral from -1 and 2 of big R squared, which is x plus 2 squared, minus little r squared, which is x squared squared, dx. Okay? Already we have a very simple problem because we don't have two integrals, we have one. So volume is pi integral from -1 to 2 of minus x to the 4th plus x squared plus 4x plus 4. Right? Yes. So antiderivative x5 over 5, x cubed over 3, 2x squared, 4x, minus 1 to 2. Okay, so that would be pi times, plugging in 2, we get -32 over 5, plus 8 over 3, plus 8, plus 8. And plugging in -1, we're subtracting that. So how many negatives do we have? We have 1, 2, 3 negatives. So it's still negative. 1/5, 2 negatives, plus 1/3, minus 2, plus 1. If I got negatives right, this is kind of what it looks like. That's 2, and 16 is 18. So if I take everything over 15, anything else, this would be 96 plus 40 plus 3 plus 5 over 15 plus 18. Okay, so everything, all the denominators now are over 15. Hopefully, this adds up to what it should. Does it? So this is 56 minus 56 minus 59 minus 54. We have minus 54 plus 270 over 15. That gives us 216 over 15, right? And you can divide both by 3. This by 3 is 72 pi over 5. Look, okay, great. That was close. Okie dokie. So this is actually easier, right? For this problem. Okay. So I'll put that on the homework. I'll put some questions in the homework assignment. You don't have to hand that in, just practice problems, where you would have to decide what is the best method to use, this washer or cylindrical shell, and of course then do it. In some problems, like in the exam or the final, you might be asked to set up the integral but not to evaluate it. Okay? Those questions, it's usually very difficult to integrate, but it's important that you come up with how to set up the integral. Okay? In the next calculus course, you'll learn other techniques of integration which will make it simpler, but you have to solve these types of problems. So it's really important for you to be able to set up a cylindrical shell problem or this washer problem very carefully. Okay? Alright, let's take a break and then we're going to do 6.3. Okay. You ready? So the idea behind arc length is very, very old. So take a circle and you want to calculate the perimeter of a circle. Then one thing you could do is you could inscribe a rectangle in it, or a square rather, and find the perimeter of that rectangle. Or you could inscribe a pentagon and find the perimeter of the pentagon. And you can go further that way and inscribe a hexagon and find the perimeter of that hexagon. As you do this, as the number of sides of that polygon increases, right, then the perimeter gets closer to the perimeter of the circle or the circumference. This idea is very, very old. Now what we'd like to do is apply that area to find the length of a curve. So here's the problem we'd like to solve. We have some curve that's given by the equation y equals f of x. And we'd like to find how long this curve is from A to B. In other words, if this were a string and it was shaped this way, I want to kind of stretch it out, put it on the ruler and measure how long it is, but I can't do that. So I have to find a way of doing that without actually changing the geometry of this curve. So one way of doing that is to just focus on one part of the curve and then try to extend that idea further. So if I just take one part of the curve and I zoom in, right? Okay. I could just consider this line segment here, because it's easy to measure the length of a line segment. Right? We have a distance formula for that, right? Okay. So what we're going to do is we can measure the length of this line segment and say that the length of this curve is almost the same as the length of this line segment. So if I were to do that, if I were to cut up this interval into many small subintervals and take the points associated on the curve with the endpoints of those subintervals, then what I could do is between every one of these 2 points, I could draw a little segment. Okay? Those orange things are segments. And as you can see from back there isn't much difference between the line segments and the curve, yes? There's slight, if you zoom in, you'll see that there is some sort of discrepancy there. But then if you make the intervals have smaller and smaller lengths, then your approximation will be much better and better. Yeah?
Yes.
Okay, so let's try to work this out. So what we'd like to do is, we'd like to say the length is going to be, is about the sum of the lengths of the segments, right? So again, I want to consider one of these. Let's say this is x sub k minus 1 and this is x sub k. Then to get the length here, we can consider this triangle. So this point is x sub k, f of x sub k. Yes? Or sorry, x sub k minus 1, x sub k minus 1. And this is x sub k, f of x sub k. Yes? All right. So what's the length of this then? The length of one segment is equal to the square root of this distance, right? Squared. That distance is f of c sub k minus f of c sub or x sub k minus f of x sub k minus 1 squared. That's the vertical length squared plus the horizontal length squared. Yes. Okay. So that's x sub k minus x sub k minus 1 squared. That would be the length of one segment. Okay. And this is the kth segment. And if I do this for all the segments, then I'll get an approximation for the arc length. Okay, but in order, my goal is to get a Riemann sum and get an integral. In order for me to do that, I would have to do it so that my integrand depends on some point that's between x sub k minus 1 and x sub k. Right? Alright. Well, again, that's not very difficult to do. So here's what we could do. I also want a delta x out here, right? I want the integrand and I want a delta x. Let's write down what I want. Delta x k, say. And then I want to figure out what is this one. Well, I know that this whole thing with the delta x has to be my arc length, or my segment length, because I'm going to add them all. So the first, here's how you can think. How do I get delta xk from this expression? Well, this is delta xk, isn't it? Okay, so I would have to bring this out of the square root, yes? Which means I'd have to factor this out, yes? When I factor this out, then this is divided by it, right? Okay, and then, so what I would get is, I would get f of x sub k minus f of x sub k minus 1 over x sub k minus x sub k minus 1, and this whole thing is squared, plus 1, times, outside of the radical, I have x sub k minus x sub k minus 1. Does that make sense? Okay, great. So I got the delta x part, delta xk rather, and this is going to be my integrand. Okay, and I still have an issue here because these depend on the endpoints, right? Okay. So now, to make this problem simpler, I'm going to assume that f prime is continuous. Okay, that's the definition of smooth. F is smooth. Okay. Is that okay? Because f is not smooth, then this wouldn't work. So f prime is continuous, which means f is continuous, differentiable, and the derivative is continuous. Okay, and here's the nice part. The mean value theorem applied on the interval x sub k minus 1, x sub k. So if you apply the mean value theorem on this interval, the conditions are satisfied. F is continuous and differentiable on the closed interval. This, then what does the mean value theorem tell us? There exists a number in here, right? Let's call that number c sub k, such that what? F prime of c sub k equals f of xk minus f of x sub k minus 1 over. Very good. Okay? Does that make sense? Okay. And this is true for every interval, right? Because f is continuous and differentiable over the whole thing, AB. So if we cut it up into pieces, I can apply the mean value theorem for each of the pieces. Yes? I can find the CK, and this is the important part, I can find the CK in each subinterval. Okay. So now going back here equals the square root, and I'll kind of write this the other way, so I'll write 1 plus. Within this parentheses, I know that there is a value of CK, so that this is basically f prime of CK squared. Right? Does that make sense? This expression equals f prime of CK for some number between xk minus 1 and xk. Does that make sense?
Yeah.
If I make the interval smaller, that CK may change, which is fine. If I make it larger, the CK may change. Point is, however big my subinterval is, or however small, I always have a C sub k for which this is true. Now, this, what did we start out with? This expresses the length of one segment, yes? So, here's the idea. Arc length, okay, we're going to add the length of each segment. Each segment has a length 1 plus f prime of ck delta x of k. And I'm going to do this for every single interval from 1 to n. And from those pictures, you see that if my subintervals get smaller, I get a better approximation. So ideally, take the limit as all the partition subintervals are all really, really small, and this will be exactly the arc length L. Yes? Without the limit, it's an approximation. With the limit, you get the exact value.
There's a square, right? In the prime inside.
Yeah, this is squared. Thank you. Okay. So, thus, we have a theorem. If f prime is continuous on AB, then the arc length is given by the integral from A to B, L equals integral from A to B. What's the integrand?
Oh.
Square root of 1 plus f prime of x dx. Squared. Prime of x squared, yeah. Very good. Okay, so that's how we find that arc length. Is that okay? All right. Here's an application. Find the length of the curve y equals the square root of x from x equals 0 to x equals 4. Oh, sorry. That's the x to the 3 halves. Y equals x to the 3 halves from x equals 0 to x equals 4. We could draw this picture. What does this picture look like? Looks like this. Okay, but we're only interested in the length from here to here. Okay, so this length. This is what we're going to calculate right now. Okay, so in order to use this formula, we need the derivative, right? So here our function is x to the 3 halves. F prime is 3 halves x to the half. Yes? And the derivative is continuous on this interval, 0 to 4. So we can use the formula. L equals integral from 0 to 4 of the square root of 1 plus the derivative squared. Yes? If you square this derivative, you get 9/4 x. Yes? Dx. Okay? And this is a pretty easy integral. We can make a substitution. Let u be 1 plus 9/4 x. Then du is 9/4 dx. And so 4/9 du equals dx. Okay, so L would be 4/9 integral. We have to change these limits. When x is 0, u is 1. When x is 4, u is 10. And we have the square root of u here. Yes? Much easier integral. Okay, this is like u to the half. Yes? So you would get u, or 2/3, u to the 3/2 from 1 to 10. So that would be 8/27. If you plug in 10, then you get the square root of 10 cubed. If you plug in 1, you just get 1. So this would be 8/27 times 10 square root of 10 minus 1. You can leave your answer like that. So that's the length of that curve. I think we did this right. There's another notation. Just a notational issue. Another way of writing this, it's basically just another way of writing what the derivative is. So it's 1 plus dy dx squared dx. If your curve is given by y equals f of x, right? It's just another way of writing it. Like prime of x dy dx. Okay, so let's do another one. Now, you should know that if the curve is given by x equals g of y, and g prime of y is continuous on CD, then the arc length is integral from c to d of the square root of 1 plus g prime of y squared dy. Okay? And of course, another way of writing that is to say that L of arc length is integral from c to d square root of 1 plus dy, dx dy squared. Where you treat y as the independent variable and x as the dependent variable. You'll just switch the roles of x and y. I mean, these two formulas are very, very similar. Okay, and the geometry is really the same. Derivation we did is really the same. Okay, let's take this example. Here's the curve. Y equals 3/4 x to the 4/3 minus 3/8 x to the 2/3 plus 5. computer to see what it looks like. But I won't try to draw it now. Okay, all we have to do is calculate the derivative and see if it's continuous on this interval. So here we would have x to the 1/3 minus 1/4 x to the minus 1/3, right? Plus 0. Derivative of 5 is 0, yes? And then we're going to have to square this, right? So let's square this before we write the integral. So if you were to square this, then you would have x to the 2/3 minus twice the product of these two, which is 1, yes? You just get half, plus the square of the last one, which is 1/16 x to the negative 2/3. Okay? And then we have to add 1 to this, so let's do that here as well. 1 plus this. But if we add 1 to this, this just changes from negative half to positive half, right? Okay. So then we would have x to the 2/3 plus 1/16 x to the negative 2/3 plus 1/2. Okay? Now, I happen to know what we need, so I'm gonna do it now. But if you do enough problems, then you'll see why this is important. What I'd like to do is I'd like to factor out x to the minus 2/3. Okay? So if you factor out x to the minus 2/3, then what do you get? You get x to the 4/3, right? Plus 1/16, right? Plus 1/2 x to the 2/3. Does that make sense? Yes? No? Maybe? Great. So no, that's not what I want to do. Sorry. This is factored. This is to be factored. Okay. So if I'm sorry about that. Plus x to the minus. Okay. So this is actually the same thing as. This is exactly the same as this with the middle sign change, right? So it's going to be the same as this with the middle sign change squared. So x to the 1/3 plus 1/4 x to the negative 1/3 squared. There we go. Okay, now the point is this is going to go in the square root, so I got to make it look nice, right? And this is beautiful because if I put this in the square root, then we're good, we're golden. L is integral from 1 to 8 of the square root of 1 plus dy dx squared, which is x to the 1/3 plus 1/4 x to the minus 1/3 squared dx. And that gives us integral from 1 to 8 of x to the 1/3 plus 1/4 x to the minus 1/3 dx. Now that's not hard to integrate. So you see where this could get a little tricky. Yeah? Alright. So then let's integrate. So if we add 1, we get 3/4 x to the 4/3 plus 3/8 x to the 2/3 from 1 to 8. Okay? Okay. So plug in 8. You get 3/4 times 16. Plug in 8 there. You get happen if this was plus 7? What would have changed if this was plus 7? Nothing. Right? Question is why? Well, from calculus we know why, because the derivative is 0 and we don't use anything but the derivative here, yeah? So any constant we put here, the answer is not going to change. Okay, that's fine. But geometrically, why is that not important? Very good. Very good. They're congruent, right? If you shift it up and down, the length doesn't change. All right? Okay, great. This is the one I want you to work on.